Hello and welcome to this 5-minute short on heat exchangers. So we've been developing a few little videos around heat loss in pipes and how to look at sort of heat transfer type effects within the Pell suite. This is the next in that kind of family of calculations that you may want to do as part of your chemical engineering life. So I'm starting off here in Flonet, and I've got a very simple little model. If you look at the heat loss through the pipes, the 5-minute short, you'll recognize this model looks very, very similar. But what I've basically done here is I've kind of said I've got a tube side. So I've got my process flow going through the tubes. I've just done very simply, an inlet node, a bit of a pipe, a heat exchanger, a bit of a pipe. Yours will be a little bit more complicated. And we've just got water going through here. And if you look down here, we can see that we're at a 10 bar gauge, about 100 degrees C. And you see there, 100 degrees C. And we're just going to cool it down with some cooling water. And to actually define the heat exchange, if I click inside here, then I've given it a fixed duty. So I'm saying I'm cool it, so I've got minus 150 kilowatts. So that's what that side of the calculation is doing. And then I might want to model also the cooling water side. Now, there's no physical link between these in the models, but this is a separate little model. I've said this is my cooling water. I've got 9 meters cubed an hour coming through, 5 degrees C. And all I've done is I've said, well, that's the same duty, only the heat's going in. So plus 150 kilowatts. And it'll go through there. So I can start to see what my inlet temperature and my cooling water supply temperature is, what that cooling water supply return will be. And similarly, I can see what it is on the tube side. And obviously that's all calculated, but with a press calculator, put that in press calculated, it will give us the results. So it kind of starts to give us that information around our heat exchanger, what the temperatures might be. So I'm going to click on their results and you start to see those numbers. Just a couple of little tips while I'm here. I've used the add text to create these tube side bits here. And then in the options on the display, you can see the bottom line. This is where I put the outlet temperature. Just double check the with format. Make sure that looks something like that. I had a few issues initially setting it up, so I was a little gotcha in there. That's how we got the model sorted out. So that's fine, but we want to actually design a heat exchanger. All we've already done is move some heat about. So what we're going to do, we're going to launch into CAPRE. And CAPRE does a couple of things around heat exchangers. So if I go to my heat transfer, I've got a simple heat exchanger, and I've got a shell and tube heat exchanger model here. So the simple one to start off with, basically going to do Q equals U air delta T. We've got 100 degrees C, so this is just mimicking what I've done in Flonet. 100 degrees C. I've got a heat capacity, a flow rate. This is my cooling water supply. Again, a heat capacity, a mass flow rate. Estimated an overall heat transfer coefficient. Now, in the calculation I did, I knew what the duty was, so I didn't know what the area was. So you can put, in effect, any number you want down there at the minute. We can decide whether it's countercurrent or co-current. Countercurrent is most common. Now I changed this area to 1, so the heat load would be 70 kilowatts. We know we've got 150. So again, using the power of Excel, we would go to a what if scenario. Now I know I want that to be 150. And I'm going to change my area up here. And there you go. I need 2.3 square meters of heat transfer area. So it's very simple of the calculation, but if you're doing some very preliminary sizing, some look-see type stuff, then that might be as much as you want to use. And we can use Excel to do the calculations we want, rather than necessarily in a sense how it was set up. Now we want to do a slightly more sophisticated example, maybe starting into some preliminary sizing. Now this is never going to replicate the the real sort of modeling of a heat exchanger, but it's going to give you that next level of detail. So for those of you, and you'll all remember course in volume 6 from your design projects, this is the method that's in there. A little bit more interesting, a few more details to put in there. So again, we've got our flow rates, shell side and tube side. We've got some physical properties. And what I've actually done now, I've started to use average values. So again, using if I go to the CAPRE physical properties tab, I've set up some physical properties down here. I've called them cooling water supply, cooling water return. I've got, there we are, moving things out of the way, cooling water return, tube side, input, exit, just to sort of, when you're clinking and doing the links, you can kind of check that this kind of makes sense. If you don't name it well, it could just be sheet 1, sheet 2. Is it the right one? So a little bit of help to trap any errors. So I've averaged the values out. Again, I've taken these temperatures off these sheets. So these were set up with the values we saw in the Flonet model. So at the minute, this is going to try and work out our temperature out on the shell side. This is what it's determining. We're going with our flow rates, temperatures in. We've got the mean temperature difference. It's worked out the heat load, so it's determined that heat load from the properties there, and that's what we wanted. So that was a good double check. We've estimated an overall heat transfer coefficient, and we've given us our preliminary area, which agrees to what we've just calculated on a much more simplistic model. So that was quite good. Again, you can play about with these a little bit if you want the shell side, tube side, all those kind of good things. Temperature out. You can work out mass flow rates as well, depending on which way you want to do this. What you're actually trying to calculate. It will look at the shell and the tube. So again, a bit more detailed than that very simplistic model. So and you'll remember things like pitch arrangements, pitch factors, tube diameters, the length of the tube. So these are just some typical numbers I've put in here. We've got our bundle clearance, baffle cuts, all that kind of good stuff. And then what it's going to do down here is actually start to calculate those coefficients in a lot more detail. So whereas before we just kind of, it feels a bit like this. This is where we're now actually calculating some proper heat transfer coefficients through our heat exchanger. We've got our fouling coefficients. So again, we would use standard references for fouling coefficients. Is our thermal conductivity for the material. So that's a sort of a good typical number for carbon steel, and actually is calculated our overall heat transfer coefficient. So we were guessing around 800 before. Yeah, we guessed around 800. Now we've actually done some proper calculations. 750, we weren't a million miles off. So calculations you would normally do, we're not talking rocket science here, but a good sort of, step up from a very simplistic heat exchanger model to the next kind of step. And then at the bottom here is when we start looking at our pressure drops through the system. So again, what would be our friction factor? 0.02 is kind of a good starting point if you want to just do something rough and ready. And it'll start to tell you what those pressure drops look like across your shell and across your tube side for that preliminary initial sizing. Just a little aside, that friction factor, you could, if you really wanted to, go and try and calculate that. So again, you could on your Flonet model, you could actually start to model, certainly the tube side, the shell side, a bit more interesting, but the tube side, you could model a tube, and you could ask the model what the friction factor is. So just to show you how that would work and some of the flexibility you've got within the results of Flonet. So I'm just going to calculate it again. We're going to click on the results. So this is the standard set of results that you get in Flonet. Inlet pressures, flow rates, etc. There's this little thing that says change columns here. And I can actually click there and say I want my Darcy friction factor. And it will add that in there. So now we were guessing about 0.2. we'd have to look at an individual tube, but, as a starting point, you can say flow through a pipe, fully turbulent. Point two is not a very daft answer. So if you wanted to do that and get those friction factors more precisely, then you can use things like Flonet to actually calculate that. So that's a little bit of how we would do some preliminary heat exchanger design using CAPRE, using Flonet in tandem, if you want to do a Flonet model as well, and get you going on your heat exchangers. I hope that helps. Thank you very much.